Welcome to a brief introduction on the fundamentals of optimization technique. So here in this very short presentation, I will try to explain the basic concepts of optimization technique. In case of optimization, what we do is we try to maximize or minimize or target to achieve a fixed value for an objective function. This objective function can be profit of an organization, that means income minus expenditure. We may try to maximize the profit, and how we can maximize? By changing either income or expenditure. So if we change these variables, we can change this objective function. Now, if we increase income and decrease expenditure, then profit will automatically maximize. Same thing if we represent this as loss, which is expenditure minus income. Our aim will be to decrease the loss by decreasing the expenditure and increasing the income. And as we are changing these variables to change the objective function, these variables are known as design variables, or in short, DV. And here P, the profit, which is a function of both income and expenditure, is defined or designated or referred as objective function. And in case of optimization problem, what we try to do is we try to either maximize this objective function or minimize this objective function, or try to achieve some targeted value. Suppose I want to say, or I want to achieve a profit of 1 crore. So how to do it? You can achieve it by increasing income and decreasing expenditure. And in this case, we will try to increase income and decrease expenditure until the profit becomes 1 crore. After that or beyond that, even if it is possible to increase income or decrease expenditure, we will stop our optimization once we reach the target value of profit, which is 1 crore. So this is, in short, what is optimization is. We also have some other concepts in this optimization. For example, there is another thing known as constraint. Look, as you know that yes, we can increase the income or we can decrease expenditure, but we can increase income up to a limit, and also we can decrease expenditure up to a limit. Beyond that, it becomes imaginary, which is not possible in real life. Or this one also. If you want to profit by selling watch, the basic manufacturing cost will be constant. The minimum cost required to manufacture a watch will always remain constant. So you cannot decrease the cost of manufacturing beyond the limit. And this manufacturing cost will depend upon the cost of procuring the raw materials, cost of hiring laborers, and cost of the fixed asset where the what I can say where the watch is being manufactured. There might be a rental cost. There might be taxes for the fixed asset, the location at which we are developing the watch. And these are minimum things. You cannot avoid this cost. So you cannot decrease manufacturing cost beyond the limit. As a result, you cannot decrease expenditure beyond this limit. So that is why whenever we try to optimize an objective function, we are allowed to change our design variables up to a limit. And this limit can be in the higher part as well as in the lower part. You can increase income up to a higher limit, and you can also decrease the income up to a lower limit. Generally what happens is we try to start to increase the income from the lower limit, and continuously we put the value of income, and if suppose this expenditure is constant, so what will happen? To increase the profit, you have to change this income. And suppose you can change between 10 to 1000 rupees, that is your income. So we start from 10 and we finish on 1000. And we find the profit for the each value of 10 to 1000. And within this, that means if we iterate, if we change 10 or if we put 10 as income, we calculate the profit for that. We put 11 as income and we try to calculate the profit for that. And then so on, we increase up to 1000 and try to find the profit. And then we compare all the profits and identify the largest value of profit as the maximum profit that we can achieve by changing only income. Now, if both income and expenditure is variable, both are design variable, then for expenditure also you can create a higher limit, and for lower limit, for expenditure also we can give a lower limit. And we always start from the lower limit to higher limit. So the thing is, when we try to increase income, we'll start increasing the income from 10 to 1000. And at that same time, we'll try to decrease expenditure from, suppose this is 1000 and this is 10, then we'll try to decrease the expenditure from 1000 to 10. So at the trade-off point, we'll find that the profit is maximum. Suppose this is the graph, and this is your income, and this is your expenditure. So at this point, profit will be maximum. Correct? So these limits is known as constraints. And if suppose you have two constraints, one lower constant, another higher constant, then the variable, the design variable is known as, or not the design variable, the optimization problem is known as bounded optimization problem, as it is bounded in both. If it is open, that means if there is no higher limit, but there is a lower limit, or there is a higher limit, but there is no lower limit, then it is said, or that optimization where the constraints or one of the constraints is not bounded in one of the side, either higher or lower, then that optimization problem becomes open or unbounded optimization problem. And also you can impose some condition like what type of value this design variable can take. For example, let us say income can be from 10 to 1000. Now, at the time of increment or at the time of iteration, what I mean is we can either we can start from 10 and then take 11 as the income, and then take 12, then 13, 14, 15, 16. So what we are doing is we are neglecting the fractional term in between 10 to 11 and 11 to 12. 12 to 13. We are not taking 10.5 or 10.6 or 10.7. We are ignoring those fractional terms. We are taking only the integers which are in between 10 to 1000. So this type of constraint can also be imposed on your design variable. Now you can say that our design variable can only take integers. Or you can say that our design variable can take both integer and fraction. That means any real number they can take at the time of iteration. And if you say that they can also take imaginary numbers, I, right? Imaginary number is a number which have a component I, imaginary component. And I is actually this minus 1, root over minus 1. So at that time, if we allow your variable to take the imaginary component also, so that can also be imposed. So when you are allowing only integers, that optimization is known as integer optimization. When you are allowing real numbers, that means both integer and fraction, then it is become real number optimization. When you are allowing imaginary numbers also, that become imaginary optimization problem. But generally, we try to impose the restriction upon the design variables which can ensure a realistic output from the optimization process through the objective equation we are using. So a realistic solution that can practically be implemented is our goal. So that is why generally we use real number optimization. We totally avoid imaginary in normal cases. And if you want to shorten the optimization process, we take only integer. But for this assumption, if we only take integer, we are ignoring the terms in between 10 to 11, and as a result, we may miss the optimal value. So, so this definition I have already explained. So optimization is defined as the maximizing or minimizing some function. That function means if it is profit, then it is this one. This is the function, right? Profit is income minus expenditure. Sometimes it is also written as income by expenditure. And if you increase income and decrease expenditure, then profit will automatically increase. So as I say, if your goal is minimization, that means to minimize the loss function. As I said, L, loss is expenditure minus loss, or E by L, or inverse to profit function. So we have to minimize loss, that is the common sense. So it becomes minimization problem. And if it is maximization, this is it. We try to increase profit. So this is known as a profit function. This is known as a loss function. Similarly, to profit function, we also try to maximize the gift function, income function, etc. Now there is, as I have already discussed, you can set a goal and try to achieve it. Now, during this optimization process, what happens is P, suppose P is I minus E is the objective equation. Now, we try to increase I and decrease E, and we try to find the optimal profit of the trade-off. Now, what our output? What is the output we can use later on? The output is actually the value of income and the value of expenditure at which profit is maximum. And now that we know at what value of income and at what value of expenditure maximum profit is achieved. So what we have to do is we have to impose strategic measures which can ensure the income and expenditure to behave as per the optimization process that we have computationally executed. That's So we have to strategize that. Suppose we have to increase income by 10. So what we have to do is we have to see whether we can increase the marginal value of the product that we are selling, or if we want, we can uh, sell the product in the same price, but we can decrease the amount of product given to the consumer. That is not ethically correct, but that can also be a strategic measure. Or we can try to decrease the expenditure by decreasing the manufacturing cost as recommended in the optimization. So the advantage is, if you want to strategize your operation in the industry after doing the optimization, the advantage is you know what income you have to achieve and you know what expenditure you have to achieve. Now note that this type of optimization process, or the entire optimization process, is a computational. It's iterated by a computer program, or by numerically it is iterated. So it is not. It may or may not yield a realistic value, but always we try to achieve a realistic value which can practically be replicated in real life. So that is why the constraints are so important. So here we are giving an example. As you can see, this is y is equal to x square. So this is y is equal to x square. this is the objective variable. I already discussed about this. Then this is x, a design variable, and this relationship is actually known as the objective function, or sometimes it is also known as objective, equation. So this is already discussed. X is the design variable, and yes, the constraints, as I have said, minus infinity to plus infinity means your none of your design variable is bounded. That means it is an unbounded problem. You have no restriction. Any value your design variable can take any value. So it is a little bit absurd. Generally, there will be a constraint. And here you see from A to B, this is our bounded constraints. This is already I have explained. Now, as I say, if one side is bounded, other side is free, then it is known as unbounded or open optimization, or single bounded. Sometimes it is also known as single bounded. If it is free in the lower side, that is the left hand side, then it is also known as left unbounded. If it is unbounded in the right hand side, that is the higher limit, then it is known as right bounded. So left is the lower limit, right is the higher limit. Okay. So all the terms had already been discussed. The only thing is that design variable is also known as design vector, and the matrix of design variables is known as design matrix. Right? So these are already I have discussed. I have also explained all the things. Object design variable are varied within the limit, higher limit and lower limit, or lower and higher limit. And the value of objective variable is noted. Y is equal to x square, right? If the limits are like this, you can vary x within 1 to 10. And let us take x only integer to shorten the optimization process. Then when x is equal to 1, y is equal to 1. When x is equal to 2, what will be y? Y is equal to 4. When x is equal to 3, y is equal to 9. Then when x is 4, y will be 16, 5, 25, 6, 36, 7, 49, 8, 64, 9, 81, and 10, 100. So if it is a maximization problem, the optimal value of y, which is found to be 100, can be achieved at x is equal to 10. This is a simple problem. It is easily known without being doing the iteration. But whenever this y becomes function of multiple variable, right? Then the optimization process becomes complex, and then you have to use some computational technique or numerical technique to solve this problem. And actually, the very term optimization technique referred to the computational program you use to optimize an objective function. And the value 100 is the maximum value that can be achieved. Keeping in view of the constraint imposed upon the input variable or design variable. This value is known as the optimal value. And at what point this optimal value is achieved? It is x equal to 10. correct? So, so what is region of feasibility and or acceptance? Now, look, this is the graph, and this is the x, and this is the y. And if I say y is equal to x squared, this is a parabolic equation. And now I say x can vary from a to b only. These are the limit. So now what? Now this region is known as your region of feasibility. That means any value of y for any value of x within this region a to b can be accepted. So as x has a constraint in its left hand side as well as right hand side. You can vary x within a to b only. So uh, so whenever x is taking a or more than a, but b or less than b, whatever value y is giving you for that, those values of x, those values of y can be accepted as feasible or permissible value. As these are for the x in between a and b. Suppose this a is 10 and this b is 100. So you will achieve the optimal point here. Y is equal to this one. But beyond that point, if you take x to be 101, y will be more than what it is when x is 100. When x is 100, y is what? Right? 10,000. But when x is 101, y is 101 into 101. And which is more than this 10,000. But we cannot take this value of y as this value of y is due to the value of x at or when x is equals to 101. And your upper limit is 100. You cannot go beyond 100. You cannot go beyond 100. So you are taking 101, 102, and you will of course get a more value of y than that is for x is equal to 100. So as our objective is to maximize the objective function y is equal to x squared, the value of y for x is equal to 101, 102, etc. is maximum compared to the value of y for x is equal to 100. But as x has a limit that it can take only the value from 10 and above to 100 or below. So when I take x equal to 101, it yield a value of y which is infeasible, not acceptable value of y. Even if it is more compared to that of at x is equal to 100, the high limit. So that is why this region is between A to B is our good region. That means green lighted region. That is your region of acceptance. But beyond 10, below 10 or above 100, This is the region that you cannot take. This is your region of rejection or region of infeasibility. But if suppose there is no limit in this side, then the entire region is your region of acceptance. But this region is still in region of infeasibility. Now, if there is no lower limit, only higher limit, then the situation changes. And if there is no limit at all, you can take any value within minus infinity to plus infinity. Then, accordingly, the limit for the region of feasibility increases. So, this is in brief what is region of feasibility and region of infeasibility. Here, you can see this picture is indicating the region of acceptance. And region of rejection. Now you see, sometimes we allow x to be equals to b. Limit of x equal to a is 1. Then any value upon this curve, this boundary is also acceptable. But if we does not allow x to be equals to b, that means our constant is like this: x less than b greater than a. Then this line, this separating line, is not under the region of feasibility or acceptability. Okay, so note this problem. When I say this, then yes, any value upon this point is also acceptable. Sorry, any value upon this point is acceptable. This But when you say this A and B, any value upon this curve is also acceptable. So this is very simple to understand, and you know, optimization. In optimization, we always try to achieve this point, the optimal point, and we note down at what value of x this optimal point is given. Look, this is the example is very simple. It is y equal to x squared. But in real life, we have to face problems which depend upon multiple variables: x, z, m, n, etc. And also, there can be some problem where there will be two objectives that you have to vary. If I take this function, this profit function, I can place it at I by e. Now, this I is also a function of many other variables. X, e is also a function of many other variables. So, but if our goal is not to increase profit, but to increase income as well as decrease expenditure. Suppose our goal is to increase income and as well as decrease expenditure. Then there is two objectives. One objective is to increase income, another objective is to decrease expenditure. That type of problem where there is two or more objectives to achieve, it becomes multi-objective optimization problem, right? Which is also known as MOP. When there is single objective to maximize, minimize, or achieve the target value, it is SOP, single objective optimization problem, or single objective problem. And if there are multiple objectives to achieve, multiple objective variable to maximize or minimize or target, that becomes MOP. So remember to differentiate this between SOP and MOP. this is what is a very brief introduction to fundamental of optimization technique, where you learned what is optimization, what is objective variable, what is objective equation, how to optimize, what is your design variable, what is your constraint, what is bounded, what is unbounded optimization, what is open, what is closed optimization, what is single bounded and double bounded optimization, and also you understood what is region of acceptance, what is region of rejection, so or what is region of feasibility and infeasibility. So all these things we have, I think I have discussed, and I have just hinted at the different types of optimization problem that we encounter while solving real life problems. So this is what I like that integer optimization technique where we can take only integer values. Then real number optimization technique where you can take real number, that is both integer and fraction is allowed. There is imaginary optimization technique. So depending on various aspects, we can classify the optimization problems to different classes, about which I will discuss later on. And if you want to participate in the entire course or entire tutorial of optimization technique, then you can purchase or you can opt for the course on data science or the course on optimization technique by myself, which is available in Instamoto as well as Gumroad. So if you are interested to take the entire optimization technique course, then you are welcome to do so. And you can either take optimization or the course on data science. In the both courses, I discuss in detail about the optimization technique. However, in the data science course, I also discuss about multi-criteria decision making, MCDM, artificial intelligence or ANN, artificial neural network, and also various statistical concepts and the basic Python that I try to include in our course. And these courses are available in data science. But if you want to know only optimization technique, yes, all these MCDM, ANN, various statistical technique, introduction to Python, and also introduction to optimization technique, and there is various classes of optimization technique. One class is bio-inspired or nature-based optimization problems or technique, where particle swarm optimization and colony optimization, bee algorithm, etc. nature-based optimization technique is also discussed. So in case of optimization, you can learn about optimization only. And for the if you want to learn more, that means you want to learn MCDM, ANN, etc., then you opt for the data science course. So with this, I conclude my presentation. Thank you for patience.